Welcome back to lecture 20.3, where we're going to discuss the central equation, aka the Gibbs equation. I think I'll call it the central equation. Okay, so this is starting chapter 6 in Finn. In Rex, he's actually added an additional chapter 6. And so this is then chapter 7. That chapter 6 is more about StatMac, which is a whole course you'll take next semester, 311. And it's best to keep it out of this one for as much as we can. Okay, so we're going to talk about the central equation, and basically we get the central equation by taking our first law. So remember the first law was du equals dq plus dw. And U is a state function, but Q and the heat and the work, the internal energy is a state function, but the heat and the work are not, right? Which is why we've marked them with their little dashes there. Now, we can turn this into an equation entirely related to state functions, right? Exact differentials. By remembering what we have written now for dw was minus pdv, but v was a state function. And we've written now that ds was dq over t, or dq was t ds. So if we combine all these things, we can write du is t ds minus p dv. And this is going to be called our central equation, or sometimes you'll see it written as t ds equals du plus p dv. All right, so why is this important? Why is this such a central idea? Well, here you can see now it's like equivalent to the first law in energy conservation, but it's entirely written in terms of exact differentials, okay? So this means, so our central equation is valid for all processes. It's valid for all paths, anything we can do, because it's entirely an exact differential. So they're all exact differentials. They're all functions of state. Saying these things, same thing in multiple ways. Okay. Okay, so let's look at this one. So it's equivalent to saying that U is a function of S and V. Right? So what we can say is, this is what we'll say is that the internal energy, or the potential energy, has, and we're going to call it natural variables S and V. These are the natural variables for the internal energy. Okay, so that is S is a function of S and V. All right, so, or sorry, U is a function of S and V. All right, so remember that if U is a function of S and V, I can, and it's an exact differential because it's a state function, I can write du is equal to partial S, partial V at constant, partial U, partial S, constant V ds plus partial U, partial V, constant S, dV. Okay, so this is just me writing this out as the exact differential. Okay, so let's compare with our central equation. All right, what do we see? Well, du is TdS. Oh, so that must mean that T is equal to partial U, partial S at constant V. And P is equal to minus partial U, partial V at constant S. Cool, we can actually see this nice relationship between a differential of the potential and the pressure and temperature, our thermodynamic variables. So we can already start to see a relationship between our energies or our potentials and our thermodynamic variables. Okay, so let's take a little math diversion. About partial derivatives. Okay. So remember, if I have an exact differential, so I'm going to call it dF. If an exact differential. If dF is an exact differential, then I can write dF, let's call it a function of two variables, x and y, is equal to partial f, partial, which one do I want to do first? X, constant y dx, plus partial f, partial y, constant x, dy. Okay, so let's just call this some variable m, and let's call this one n. Sort of like what we did over here. We called this one t and this one p. Okay, so we're just going to make it general. So I can actually take what's called a mixed partial. So what I mean here is, so what I did here was I took the derivative. So this is partial x of this function f, right? But I could also take the derivative with respect with y afterwards, right? Because m could still be a function of both x and y, and n can still be a function of x and y. I just held y constant for it. Okay, so I can just take the derivative with respect to x and then later take it with respect to y. So we would write this as partial squared f, partial y, partial x. All right, so if you were to have written this, or, you know, if these were both x, we would have written d squared f dx squared, right? But these are two different variables we're taking the derivative with, where these are partials. All right, so we can write this as partial y of partial f partial x at constant y. But remember, this all has to be taken at constant x, because I'm now, turns out this object doesn't matter if I switch the order of taking those derivatives. Because when I held one constant and took the derivative, and then I took another and held it derivative, constant and took the derivative, it's totally equivalent to writing partial x, partial f, partial y, x, all of constant y. Or partial squared f, partial x, partial y. So the order of my partials doesn't matter in my mixed partial. Okay, so now let's realize that this is what we defined as m above, and this is what we defined as n above. Right? So now I can write that partial m partial n at constant, partial n, partial m, partial y at constant x is equal to partial n, partial x at constant y. And this is called the compatibility. Compatibility condition. And it's really equivalent to saying that we can do our mixed partials in either order. Okay, so armed with this, remember we had our t was equal to partial u, partial s at constant v, and p was minus partial u, partial v, constant s. So now we can write these in terms of this the mixed partials, right? So let's write partial v, partial u, partial s, constant v, constant s. Just to keep my bracketing the same, is equivalent to partial s of partial u, partial v, constant s, constant v. Or this says partial T, partial V, right? This is T at constant S is equal to partial minus partial P partial S at constant V. And this is the first Maxwell relations. So we're going to have 4 Maxwell relations, and this is our first one. This is completely general. And it holds for any system. Okay? And it's really equivalent to our compatibility, right, condition. We can either think of it as our mixed partials here, or we can just write it down from our compatibility condition by finding the relevant things. Okay? It really is about, it's equivalent to our mixed partials, but we can write it down quickly from our compatibility condition. So what we're going to do next time is we're going to write it down for our other relations. So we did our internal energy. We'll do our other relations in the next section.